It's like the North Pole in here today. Close the door, Leah.
Don't do that again. We're missing it now.
You're just in time. We're thinking about what to investigate. And you've given me a good idea. Let me see. I think I'll set you a puzzle first. Switching to replay. What has this man got to do with these aircraft? And what have these aircraft got to do with my favorite racing car? And what have these birds got to do with our special investigation today? Well, the answer is they're all to do with air at work. Do you remember when you did this, Leah? Surprised you, didn't I? The air pressure on that piece of newspaper holding down the ruler was heavier than the force of your hammer blow. Amazing. And I know you remember this, Piers. We boiled most of the air out of the can, and when we put the lid on, the force of the air pressure in this kitchen did all that damage trying to get back in, because it wanted to fill the empty space. Extraordinary power. I'm switching to replay to show you something else you'll remember. Air moving from one place to another causes the weather to change. If there's a low pressure area on the weather chart, the air rushes in to fill it, and that's what causes wind. Long ago, people learned how to use the wind to work for them. Windmills are just one example. You can even use the wind to have fun. Air that's moving is useful stuff, no doubt about it. The fan has got those half ping-pong balls working all right. They're really moving. And that tells you how fast the fan is going. And your weather vane, Piers, tells us where the fan is, where the wind is coming from. From an area of high pressure made by the fan to an area of low pressure, the rest of the kitchen. Switch off and make the pressures equal everywhere, and the wind stops too, just like the weather. A hairdryer and a balloon. Why doesn't the hairdryer blow the balloon away? Why is it just sitting on top like that? It's being held there steady as a rock. Try it with a ping-pong ball. It's just got to stay on top of the air for some reason. Looks as if it would stay there forever, providing you didn't switch off the hairdryer, Tom. The column of air shooting out of the hairdryer is creating differences in the air pressure all around the ball, and it's trapped it in that position. I've got something to show you. Switching to replay. Remember this face? He's Daniel Bernoulli, and 200 years ago, he worked out exactly what happens when air and liquids move very fast. My assistant can show you what he discovered. It's very simple. That green fluid is being pumped through the glass tubes, which are all interconnected. But the supply to the middle tube is pinched off on both sides, and that makes quite a difference. She's going to measure that difference with a ruler. She's measuring the pressure differences in the upright tubes. The fluid in the middle tube, the one with the squeezed-in supply, hasn't risen as far by the look of it. And that's what Bernoulli discovered. The faster the flow of fluids or air, the lower its pressure will always be. That's why a compressed air spray works. Switch it on, and air rushes across the top of the tube carrying the liquid, and the pressure there is lowered, and the compressed air forces the liquid out in a fine spray. You can do the same thing with a bottle and 2 straws. One straw is sticking out of the fluid, the other is at right angles to it. All right, are you ready? Blow across the top of the one in the fluid, the low pressure tube, and up it comes in a fine spray. That's the Bernoulli effect. And here's another way to show the same thing. Put that penny next to the plate, Tom, and try to blow it in. Well done. The trick is to blow very fast just above the coin. The fast-moving air will produce a lower air pressure above it and suck it into the plate, like that. A fast-moving stream of water does just the same thing. A ping-pong ball on a string, and place it under the tap. The water speeds up as it goes round the ping-pong ball. The pressure lowers, and the normal air pressure in the kitchen pushes it into the water stream. Can you feel it tugging at the end of the string? Your turn, Tom. Hold the paper near your lips and blow across it. The air pressure lowers and up it comes. Now you, Leah. Stick your sheet of paper in the book, and you can use the hairdryer to lift it instead. That'll do. Switch on, and lower the pressure on top of the paper with a moving stream of air. And there you are, Bernoulli's law again. And do you realize that all these experiments have been giving us clues to why aeroplanes can fly? Why aeroplane wings are shaped the way they are? Where are those shapes we were making yesterday? That's the one, Tom. A single piece of card with a fold that is not down the center, so one side is longer than the other. Then, when you stick the edges together, you have a shape rather like an aeroplane's wing. Let me see. Yes, that's right. Very neat. It's called an Aerofoil section. The top, which is curved, is quite a bit longer than the bottom, which is straight. Aircraft designers spend a lot of time studying this shape. Disc number 10, please, and I'll show you. This is a small wind tunnel. I'll turn it on its side so you can see what's happening better. There's an aerofoil, like the one we made with cardboard, and those white lines are streams of smoke so you can see what the wind is doing. Watch those little bumps in the smoke. As they pass over the longer upper surface, they speed up, can you see? And the ones underneath slow down. Where the air is speeding up, there's a low pressure area. Remember the Bernoulli effect? And the aerofoil is being lifted into it. In this special picture, you can see exactly where that low-pressure area is centered, just where that red dot is on the top. And that's why aircraft wings are that shape. When the air passes over them, they automatically get pushed up into the low-pressure space, and it helps them to fly. We'll get our own wind machine going. Set the fan up, and we'll test one of the aerofoil sections we made out of cardboard. The aerofoil is fixed to one end of a piece of wood, which is weighted with plasticine at the other end to balance it. Rest it on its supports. That's it. And the big question is, will it fly? Switch on, please, Tom, and we'll see. Yes, we have liftoff. It's Mr. Bernoulli's law at work again. The wind from the fan is racing over the top faster than it's passing under the bottom. So the whole thing is being lifted into the low pressure that's being created. That's right, Leah. The low pressure area on top of the wing. And that's where the high pressure area is. But what would happen if we changed the way the aerofoil is facing the wind? Switch off the fan for a moment, Tom. Down it comes. And Leah, bend the whole thing downwards. Increase the angle. That's right. Now switch on again. Look at that. It's flying much better. It's almost twice the height. Switch off again, Tom. Yes, go on, switch off. And bend it even further now, Leah. That's right. Now what'll happen? Fan on. And it hardly gets off the ground. There's no lift anymore. Now what has happened, do you think? Obviously, that angle doesn't produce a low pressure area for the aerofoil to get sucked into. Let's go back to the wind tunnel. Switch to replay. Flying nice and steady, but watch this. As the angle increases, it gets to the point where this happens. It's called turbulence, and the low pressure area on the top is destroyed, and the thing can't fly anymore. If that happens to an aeroplane, it stalls and starts to drop until the angle changes, and the low pressure area on top of the wing returns and pulls the aeroplane back into the air again. So turbulence is when the air stops working for you and starts working against you. This flat plate was never meant to fly, but look what happens to the air around it as it faces more and more into the wind. This is one of the most extreme kinds of turbulence you can get, and all because of the shape of the flat plate. Aeronautical engineers call it drag, and it's easy to see why. Even with a smooth shape, there's often a lot of drag. The air behind it doesn't know which way to go. It's tumbling all over the place. Let's try an experiment. 3 bricks with different shapes of cardboard attached to them, an aerofoil in the background, a cylinder in the middle, and a square plate facing into the wind. Switch on, Piers. Not much doubt which slices through the air best. The aerofoil at the back. The other two are dragging badly. Drag and turbulence certainly slow things down. You don't have to have a fan to experiment with turbulence. Anything, any shape that will slow down the air will do. cotton reels on a nail stuck in a bit of wood. Wind some string around them with a weight on the end. Plasticine will do. And you can do a drop test. Ready? Let them go. Not much drag there.
The same. You started a bit late.
Let's do it again, but this time, Sylvia, wedge a card in the slit on your cotton reel. There's one on the table, I think. Wedge it in firmly. Ready? Now let them go again.
Mine.
It's slowed down quite a bit. If you were a car designer, that's the kind of thing you'd have to know all about so your design wouldn't drag. Disc number 10 again, please. In this huge wind tunnel, they're using smoke again to see what happens to the air as it flows over this shape of car. They want to see if there's any turbulence or drag. Well, it seems as though they've got a good shape here. The air is slipping over it nicely. And that's why objects designed to go quickly through the air, like this train, have a smooth, streamlined shape. At high speed, the air just slides over it with the minimum of drag to slow it down. You can see that they've been careful not to design any bits that stick out from the side of the train, because they'd cause drag and make turbulence. This shape has been created especially to slice through the air as cleanly as possible, with aerofoils to help it. And what about this for streamlining? It's this shape because it's designed to travel through the air very fast, with the minimum of drag and turbulence. But sometimes, turbulence and drag can be made to do a useful job. Ready with that parachute, Piers? If you were a parachutist, you'd make very good use of drag to slow you down.
Oh, it did work.
Disc number 10 again, please. Switching to replay. The spacecraft that went to the moon returned to the Earth's atmosphere at 40,000 kilometers an hour, and the best way to slow it down was to use air resistance. It was going so fast, the friction of the air caused part of the spacecraft to burn, but it was designed to do that. That's air resistance doing a useful job. And when it had slowed enough, yet more air resistance to act like a brake. A set of small parachutes slowed it down even further. And the final air brake, 3 huge parachutes that reduced its speed so it could plop gently into the sea. So air turbulence and drag have their uses if you want to slow down. They can be used as very effective air brakes. This aircraft makes use of drag to slow it for landing. Look at those fins that have unfolded at the back. And the panels on the top of the wings. They're dragging through the air and bringing the plane to a stop by creating drag and turbulence. Of course, it's not an original idea. Look at the way this chap uses his tail and feet to land. The first people to fly figured out a way to use air to push them along. Now, how's it coming along over there? Are you ready to take off? Yes, they used propellers, of course. Let it go, Leah.
Ready, steady, go.
Oh, you'll have to wind it up more than that, Tom. A propeller pushes a column of air backwards, which makes the aeroplane go forwards. Switching to replay. Here's the very first aeroplane built by the Wright brothers in America and flown in 1903. Nowadays, planes are more streamlined, but they still use propellers to push the air backwards to make the plane move forwards. Wow, look at that. Remember the first time we did this? That's how we used air for jet propulsion. Now watch this. Switching to replay. Look at those jets. White hot air pushing the plane forwards until it's fast enough to take off. Up she goes, on the end of a jet. Here's the most basic kind of jet in action, a rocket, producing an enormous lifting force. Still winding, I see.
Take a long time to wind up, don't they? Easy, good. Woo!
That's it, wind them up really tight. Okay, Syria. Yes, not bad at all. Who's next?
I think mine's ready now. Mine's ready. Oh, come on, dear. That seems to have done well. Yes, I hope. Mine's almost ready. Oh, yours is very good. What's that? Oh, yes!
That's a good one. Lots of lift in those wings. Oh, look out, here it comes again. Yes, you've certainly got the air working for you now, all right.